Hello, everybody. In this video, we want to talk about the graphs of logarithmic functions. So we're definitely going to use to leverage the fact that the logarithm and the exponential function are inverses of each other. So if you look at this picture that we have right here, um, this blue graph is the curve y equal to 2 to the x. And what are some nice properties that we know about this? We know that the y-intercept point here is going to be 0, 1. Let's label one more point. We know that this point right here is going to be 2, 4. Okay. And we also know that there's a horizontal asymptote. And that horizontal asymptote is going to be this line here. I'm going to use a dashed line to draw that horizontal asymptote. So let's do that like this. So this horizontal asymptote has the equation y equal to 0. Okay. If you look at this um, dotted green line, this dotted green line is the curve y equal to x. And we learned before that there's a relationship between the graph and its inverse. And its inverse is obtained by flipping this graph across the line y is equal to x. In other words, when you flip across the graph y equal to x, we're going to interchange the x and y values. So we interchange x and y to get the graph of the inverse. Okay. So let's flip each of those points one by one. Um, if you took 0, 1 and you interchange the 0 and the 1, you would get 1, 0. So that point moves to 1, 0. Okay. If you took this point 2, 4 and you interchange the x and y coordinate, that would give you 4, 2. So that would give us this point right here. Now you ask yourself, what happens to this horizontal asymptote when we interchange x and y? Well, what that would mean is that you're going to replace this y with an x. So you're going to get x equal to 0. And x equal to 0 is the graph of a vertical asymptote. So if I were to do that, then I would get the following. I would get this vertical asymptote here, like this. And I could label that as x equal to 0. Okay. So this orange graph that we've just drawn with this new vertical asymptote, this is the graph of the inverse of the exponential function. So this is the graph of the logarithm. And just as a reminder, the inverse of 2 to the x is y equal to log base 2 of x, like that. Okay. So if we were to analyze, um, some of the relationships over here, what will we see? Well, we see that the domain of the exponential function went from negative infinity to positive infinity, right? And that domain now becomes the range. Sorry. What about the range of this blue graph? Well, earlier we saw that the range of the blue graph was from 0 to positive infinity. Okay. Now let's look at the graph of our inverse. When you look at the graph of the inverse, which is this orange graph over here, we see that we never get negative values. That's super important. We have a vertical asymptote, so you never even hit 0, and the domain is going to be all the values of x that are greater than 0. So we're going to put this as 0 to positive infinity like this. And notice the fact that these two are the same. In other words, the domain of the inverse is the same as the range of the original function. that is going to be true in general. If you look at the range of this logarithm, every single y value here is going to be hit. I know that this graph is growing very slowly, but it does continue to grow. It just grows extremely slowly. So for the range of the logarithm, that's going to go from negative infinity to positive infinity. Of course, those aren't real numbers, so we put round brackets there. And I'm just going to remind you of the general comment that the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. Okay, so we can see that very clearly here. We should list some key features. We've already looked at or discussed some of these features as we graph this guy. So the first thing I would say is that the x-intercept is going to be 1, 0. And that's because the y-intercept of the original function was 0, 1. The vertical asymptote is going to be x equal to 0. We can see in our picture over here that this graph is always increasing. And that is because the graph of our original function over here was always increasing, and we just flipped it. So it's increasing when the value of b is actually greater than 1. Okay. And if you were to look at our graph from the very beginning, if you were to look at this this orange graph over here, and you were to invert it about the line y is equal to x, the graph would look something like this. It would come down something like this. So we can see that when we invert the orange graph, you're actually going to get a function that's decreasing. So if we go back to these key features, the function is decreasing when this constant b is between 0 and 1. Okay. So I guess I'll just make a comment. Graph is graph, let's say, of the logarithm log base b of x is either always increasing or always decreasing depending on the value of b. All right. The final thing, when you look at this graph, does it pass the horizontal line test? It certainly does. So since it passes the horizontal line test, it is 1 to 1. So we could say passes the horizontal line test. Another way you could see it is, you could see it's always increasing. If a function's always increasing, it can never get the same y value twice. So that means it's going to be 1 to 1. Of course, it's always increasing if b is greater than 1. It's always decreasing if b is between 0 and 1. Okay. So that pretty much covers the graph for the logarithm. One final thing I'll say is that when the base is bigger than 1, the graph always has this general shape like this. And when the base is between 0 and 1, it'll have this kind of shape that comes like this. And the different bases just kind of change the severity. So, but it has the same basic shape. All right, everybody. I'll see you soon.